Welcome to BYJU'S Exam Prep GATE official YouTube channel. We are seeing the topic deformation of tapered bars due to axial load, and we are covering this topic under the capsule series. My name is Satyajeet Sir and I have done my BTech and MTech both from IIT Kharagpur. So let us start the topic. We know that if we have a bar like this and we are applying an axial load. If you are applying an axial load, means what? The load direction is along the longitudinal axis of this particular bar. And suppose the load is P kilonewton, the length of the bar is L, and suppose the cross-section area of this bar is A, and the modulus of elasticity of this bar is E. Then the deformation, this I will call as what? The axial deformation equation is equal to what? It is equal to PL upon AE. This is the equation for, we can say, expression for deformation of bar under axial load. Now, if we have a circular bar, now when I say a circular bar, what does that mean? That means that the cross-section area is circular. So, the lateral dimension will be what? Diameter. So, this is what? The diameter. Okay, the diameter of the bar. Now, if we see the deformation of such a bar under axial load P. Suppose we have axial load P acting on this particular bar. Okay, suppose we have axial load P acting on this particular bar. Then what will happen? The deformation equation we just saw, it is PL upon AE. Right? Now you see, this is P, this is L. In place of area, what I will write? You see, the diameter of this bar is D. Circular bar. So area will be how much? The area will be simply pi by 4 into d square. So here I will write down pi by 4 d square into E. So the deformation will be how much? It will be 4PL by pi d square into E. So this is the expression for finding the deformation of a circular bar under axial load. Now you see, this circular bar has constant cross section. This circular bar has what? Constant cross section. Means what? The diameter is uniform throughout the length. But if the diameter is changing, then I will call that as what? Tapered bar. And it will look something like this. This is what? Tapered bar, or can say circular cross section with varying diameter. So if you cut a cross section here, if you cut a cross section, it will look circular only. But you can clearly see that the diameter is changing from D1, right? It is changing from what? D1 at one end to D2 at other end. And the force is P and the length is L. So how to find out the deformation of this particular type of bar, a tapered bar? I'll call this as what? Tapered bar, where the cross-section area is changing. Now why it is changing? Because the diameter is changing, right? So I can say that for this tapered bar, I will have a very simple conclusion. A very simple method I will tell you. So all the students who are watching it live, okay, it's very simple. You see, this is a bar of uniform cross-section, right? This particular bar is of a uniform cross-section. What is deformation formula? 4PL by pi d square into E. This formula we just saw. This is for, I can say, this is for a uniform cross-section. For a uniform cross-section, circular cross-section. Now if we have a tapered cross-section, very simple. Write down the expression. The expression is what? Same expression as this. 4PL by pi d square into E. In place of this d square, write down what? d1, d2. Very simple. In place of this d square, write d1, d2. You got your expression. You got your expression for deformation in a tapered bar due to axial load. So if you know this, you know this also. In place of d square, you just replace that with what? With d1 and d2. Very simple. Let us solve a very simple question. Okay, a bar of 300 mm length. This is the length. Circular cross section area tapers from diameter 60 mm to 40 mm at other end. If the bar is subjected to a load of 60 kilonewton, okay, and the E is this, okay, we have to find this extension. So directly I can use the formula, right? Yes. Directly can use the formula. It will be how much? 4PL by pi. In place of d square, use what? d1, d2 into E. You see, this is your d2, the higher diameter. This is d1, right? And this is your P. Now see, if you want to find out the deformation in mm, then express everything in Newton mm. So your deformation in mm will be equal to how much? 4. In place of P, it is 60 kilonewton. You can write down what? 60 into 10 to the power 3 Newton. The length is how much? 300 mm divided by pi. D1 is how much? 40. D2 is 60. And E is given 2 into 10 to the power 5. If you calculate this value, you can calculate yourself. I have already calculated it, and the value is 0.047 mm. Right? So you see, by just remembering this formula and how to remember also I explained to you, you can easily solve questions like this. Now let us solve a question which is frequently asked in your GATE and other examinations in ESE also. Okay? So this is a question. A bar of length L of circular cross section tapers from 2D at one end, okay, to D at other end. Okay. Find the percentage error if average area is used for calculating the extension. Now this particular question is asked a lot in many examinations, so we'll have a generalized equation. Suppose this is D1 and this is D2. Now what is asked? Find the percentage error if average area is considered. See, if average area is considered, what will be average area? It will be your, I can say that average area means I will consider average diameter, right? So if I consider average diameter, what will be the average diameter in this case? The average diameter will be equal to how much? Your D1 plus D2 by 2, right? This will be the average diameter. So they are asking you, if you consider the average diameter, what will be the error percentage? Now understand that it is not correct to take the average diameter, right? Because the actual expression was how much? It was 4 PL by pi D1 D2E. This is the actual deformation, right? I can write down actual deformation. Now if you consider the average diameter, okay, and then find out the expression, that will be the error one. So this will be what? This will be the error one, and this will be equal to 4 PL pi. You're considering what? Average diameter. So D1 plus D2 by 2 whole square into E, right? So they're asking you that this is the actual one and this is the error one. So what is the error percentage? That's very easy, right? We know that error percentage will be what? That will be the actual the deformation minus the error one divided by what? The actual one into 100. Now I will derive the generalized expression, and you can see that how fast we can solve questions. So this will be equal to, I can say, this will be equal to, you see, the actual one was how much? 4PL by pi D1 D2 into E. And the error one was how much? 4PL by pi d1 plus d2 by 2 whole square into E divided by 4PL, what is the actual one? Pi d1 d2 into E, and then into 100 I can do. Now you see, in the numerator denominator I can cancel this 4p, 4p, 4p. Actually I can cancel the whole 4pl. Pi, pi, pi I can cancel. E I can cancel. So what will happen? This expression will change to, if I erase all these things, this expression, okay, will change to what? This particular thing, right? It will change to this. Now you see, this numerator I can multiply like this, and this will become what? If I take common, it will become d1 plus d2 by 2 whole square minus d1 d2. Now you see, this d1 d2 gets cancelled, so I can just erase this, right? Yes. See the expression now. This is equal to, I can say that d1 square, I'll open the bracket, d1 square plus d2 square plus 2 d1 d2 divided by what? 2 square will be 4, right? 4 minus d1 d2 in the numerator. Now you see this 4, if I take 4 common, this will become what? 4 d1 d2, right? Here this will become 4 d1 d2. Now if you subtract this 2 d1 d2 minus 4 d1 d2, it will become how much? Minus 2 d1 d2, right? Now see, and denominator we have what? d1 plus d2 whole square, and then 2 square is 4. This 4 get cancelled. What is this? This is d1 minus d2 whole square, right? So the whole expression changes to, very important, what? d1 minus d2 by d1 plus d2 whole square into 100. Now you remember this. See, the derivation is not important for you for the examination. That was just for your reference. Okay. So you see, the error percentage, if you consider average diameter, is this. So now anything they give you in examination, you can easily find out. So now coming back to the question. You see, this is d2, this is d1. So the error percentage will be how much? The error percentage will be d1 minus d2, or I can say d2 is more, so I can take it d2 minus d1. Doesn't matter, right? Doesn't matter, because we are making it square. So d2 minus d1 we can say, right? And this will be what? I can say d2 plus d1. Doesn't matter, right? Because we are making a square of this. So now the error percentage will be what? d2, 2d minus d1, d by d2, 2d plus d1, d, right? Whole square into 100. So this becomes how much? 2d minus d is d, and this is 3d, right? Whole square. So dd get cancelled, becomes how much? 1 by 9 into 100, and this is close to how much? I can use the calculator. Okay. Anyhow, it will be 11.11, just cross checking it. 11.11. Now you see, this was the question given here. If they change the question, just give some random thing. Suppose they are telling it is, the tapering is done from 3D to D or D to 3D. Then also you can find out the error percentage, right? By just using this formula. You see, here this will become D2 and this will become D1. So D2 minus D1 means what? 3D minus D. So 2D by what? 3D plus D is 4D, right? Whole square. So what will happen? DD get cancelled. This is 2 by 4 is what? Half, right? So 1 by 4, right? Into 100. Making it how much? 25% rise, right? See, very simple. 3D minus D by 3D plus D. So 2D by 4D. And whole square, obviously. Okay. So 2D by 4D means what? 1 by 2 whole square. So 1 by 4 into 100 is 25%. So like this, anything they ask you in the examination, you can easily solve, right? Anything they ask you in the examination, you can easily solve that. Yes. Now see this question. The question is, a bar of length L is having circular cross section and it tapers from diameter D1, D plus A at one end to D minus A. So this I can take as D2 and this I can take as D1 because smaller one. Find the percentage error if average diameter D is used for calculating the extension. Yes. So now the same formula, the error percentage will be how much? D2 minus D1 by D2 plus D1 into 100. So such kind of question you can easily solve. Don't forget the square. So this will be how much? D2 is how much? You see, D plus A and D1 is D minus A. So when you take this minus and it is D minus A, when you open the bracket, it will be how much? Minus D plus A divided by D plus A minus, not minus, plus D minus A. So here AA gets cancelled, here DD gets cancelled. And this is square, right? So this becomes what? Numerator 2A, right? It becomes 2A, it becomes 2D. So what? Both get cancelled. A square by D square. Yes? A square by D square and into 100. You see, so fast you are able to solve such kind of questions if you know these concepts and these short formulas. So this is the right answer. The first one is right answer, right? You see, the first one is your right answer, right? Now this was for a circular cross section. If you have a rectangular cross section and the width is varying, you see this is having rectangular cross section, means what? Is having length L and this is P, okay? And this is your thickness of that particular rectangular bar. You see, if you cut a cross section here, this is the thickness and this is the width, and this width is changing, right? You see, here it is B1, right? And here it is B2. Now how to find out the expression for this? Very easy. Suppose we have a rectangular cross section only, but the width is constant. Suppose the width is constant. If the width is constant, what will be the deformation equation? The deformation will be PL by A only. And what is area? Area is width into thickness, right? You see, area is what? The area for this is what? Width into thickness only. So here I can write down what? In place of area, width into thickness, right? Yes. Now for this bar which is changing from B1 to B2, just remember this. Write down the formula PL by BTE. The same formula for what? Write down the same formula for your uniform cross section, uniform rectangular cross section, and this is tapered cross section, means changing width. Write down the same formula. In place of B, write down what? B2 minus B1, right? Divide by, write down what? B2 minus B1 divided by ln B2 by B1. It's very easy, right? Yes. So now what is the expression? You see, this is nothing but PL by, write down the same thing, TE. In place of B, writing what? B2 minus B1. Now the division will go up, right? Making it what? ln B2 by B1. Beautiful, right? Very good. You see, so easily you are able to remember this formula. See, this can be written as like this also, right? You see, B2 minus B1 by ln B2 minus ln B1. So easy to remember, right? B2 minus B1 by ln B2 minus ln B1. Now what is ln B2 minus ln B1? That is ln B2 by B1, right? Log properties. Yes. So you can remember the formula for a tapered rectangular cross section also so easily, right? Now you see, we'll solve a short question. You see, a steel plate of thickness 10 mm tapers from 60 mm, I can say this is B2, to B1 40 mm on the other end, and the length is given 600 mm. It is subjected to a load of 60 kilonewton. Find the extension. Directly I can write down this as what? PL by B2 minus B1, right, into T into E ln B2 by B1. Just put the values. P is how much? 60 into 10 to the power 3, right? Length is 600. B2 minus B1, you see, B2 is how much? 60. B1 is 40. B2 minus B1 is 20. What is thickness? 10 mm. E is how much? 2 into 10 to the power 5, right? And this is ln. B2 by B1 means what? 60 by 40, making it how much? 60 by 40 is how much? 6 by 4, 3 by 2, ln 1.5. You can solve this. Let me solve for you, okay? Let me solve for you. So this is ln 1.5. I'll multiply 60 into the power 3 into 600 divided by 20 divided by 10 further divided by 2 lakhs. I'm getting a value almost equal to how much? 0.365 mm. So in this very short capsule video, we covered the deformation of tapered bars under axial load. Thank you very much.